Good afternoon. Thanks for coming here. My name is Srinivas Nemagadda. Along with my colleague Rupesh Warrior, we're excited to share our experiences in migration of our large analytics platform from MPP database to Hadoop Yarn. So that's the talk. So before I get started, I just want to just go over a few things. MPP, basically, it's a massively parallel processing, technology that's very popular in the last decade or so. Why are we migrating? What is driving us towards, Hadoop? What is Hadoop doing it for us, right? So essentially, there is a difference in the technology. Hadoop is providing a truly open source distributed, computing paradigm. The key drivers for going towards Hadoop is, number one, it is open source. I'll elaborate what open source means for us. It's not only doing traditional analytics, but also it opens up possibilities for a lot of other things that we can do along with analytics. Then Hadoop is also providing scalability, reliability, and other aspects that typically one would look at the platform. So there are some key drivers that made us look at Hadoop and make this transition from MPP to Hadoop Yarn. So before I get going, I just want to get a quick pulse from the audience. How many of you have already some sort of Yarn deployment in your environment? Few, great. How many of you have MPP databases and thinking about analytics? Great. Oh, quite a few. I'll be happy to talk to you, more details about your experiences and your thoughts after the talk as well. So here I'm going to share with you our journey, and then I want to highlight one important thing here. MPP to Hadoop is not like you flip a switch one day and then it happens. I would consider this is more like a journey. It's a transformation. That means we will figure out what are the components of MPP that are really running hard, that doesn't make sense in the MPP world, but we need to transition to Hadoop. So you gradually transition component by component into Hadoop or big data ecosystem, right? So that's the approach. So it's not a one-time switch. And then the second thing is it is consider this more like a journey, right? The destination here is we are embracing open source. We are embracing truly distributed computing and the advantages that Hadoop brings us. So with that, let's get started. So the way I arrange the flow of our talk here is these 5 things. So I want to introduce briefly about our group, what we are doing, the big data needs we have at Symantec, and then give you an overview of our MPP platform, and then how we are planning or we are working on transitioning that to Hadoop, how the new platform looks like. And then we'd like to share our experiences along the journey. So before we get started on the actual topic, let me give you a brief overview of Symantec and the cloud platform engineering, the group that myself, Rupesh, and the team is working on. So it's a greenfield opportunity for us. The Symantec CPE organization is responsible for building the data centers, the network behind them, creating the platform services, and operating them. So who are the consumers of the platform services that we are building? Mainly internal Symantec R&D teams, which are developing security products, data management products, and everything that we offer to our customers. So what we have done is we have taken OpenStack, open source approach. Basically, we have chosen Hadoop for analytics environment and OpenStack for our cloud and computing environment. So what we are doing here is, as part of the CPE, we are bridging the gap between these two very important open source technologies and creating our platform offerings on top of it. So what does our platform offerings do? It's kind of a marriage between cloud and big data, and then we are solving how do we provide secure multi-tenancy if somebody is building an application that spans not just analytics, but also services that are offered in cloud, integrated seamless multi-tenancy across both environments. How do we do it? How do we make sure that these services operate in a reliable fashion? Reliability here not necessarily mean within a cluster, but across the racks and within a data center, across the data centers and so forth. So those are all the aspects that we add value as part of the Symantec CPE cloud platform that we are building. In terms of analytics, why is it important for us, right? So we at Symantec, we have products that we offer to consumers, we offer to enterprises, right? So we have managed security services using which we protect the enterprise premises. Many of you are familiar with our brand Norton Antivirus, and there are a whole suite of products under Norton, right? So all these products that we offer underneath, they use different types of technologies. An example of that is reputation-based security. If you Google it, you'll find a lot of information about it. So these technologies, whether we do the fraud detection or when our applications or appliances call back home with the telemetry, they generate a lot of data, right? So how do we actually consume this data, manage it? So that was the past problem. But what's happening is recently that volume of the data is actually increasing. But not only the volume is increasing, but also the time in which we actually process the data, extract the value, and then provide the information back to the consuming application. So these applications become smart in close to real time. So here we are grappling with two dimensions, the space dimension, the volume, and the time dimension, right? So obviously, using MPP databases creates a challenge. And that's one of the drivers for us to embrace the Hadoop-based true distributed processing. So with that, so let's just take a quick look at our big data challenge, what it means, right? So at a higher level, so if we have applications that are deployed across multiple consumers, millions of consumers, and then enterprises, what we have is, imagine like you have millions of users, and these users are working in an environment where they are touching directly or indirectly billions of files. We need to figure out if the file is good or infected, not good. Our consumers or our customers are touching millions of URLs. Is the URL safe or not? They are accessing and working on thousands of applications. Is the application stable? Is it crashed? Is it crashed because of some virus problems, right? So what does this mean to us eventually, right? So we are getting a lot of data from these applications and services in real time across the globe, a constant feed of information. So what does this mean, right? This means a lot of volume of data. So Symantec, we have historically collected multi-petabyte data coming from these various sources. And in addition to the historical data, we call it as security metadata. In fact, we have one of the world's largest security metadata in house. In addition to that, these applications are generating multiple terabytes of daily incremental data. So we need to ingest this data and then process it in close to real time. The data is in wide variety of input formats. Some of it is structured, some of it is semi-structured, and so forth. So the challenge is, how do we manage it, right? So here you see data piler. You can see, you can call it as a data lake. And then on this data, what we do is run a wide variety of jobs. We do ETL jobs to actually load the data into our system. Then we do daily incremental batch operations to transform the data from one format to another format, derive additional value. And then our analysts and security researchers, they do interactive ad hoc analysis, right? So there are different types of workloads that we have on this data. So the key challenge for is, how do we extract value from volume in real time? So that's a problem that we are facing, right? So what we have, the legacy solution is as follows. What I'm going to do is in the next slide, just explain briefly the higher level architecture for our MPP platform. So here at the core, we have a traditional MPP engine. So what you have is a cluster of segment database servers. And then on top, you have 2 nodes, you can call it as master controllers. All they are doing is just taking the query, incoming typical SQL query, parsing it, segmenting it, and distributing the query to multiple engines. So that's how the traditional MPP databases work. And then what we have is on top, we have raw data sources. As I mentioned earlier, we have incremental data coming every hour, every day, and so forth, right? So we ingest data from different sources all across the globe, right? We have roughly like 24 data sources. We need to, for compliance reasons and other various software engineering reasons, we need to keep a copy of the data as we ingest in our system. So we call it as a raw data store, RDS for simple words. And then from the RDS, in the legacy system, to keep the data, we have a separate NFS-based RDS cluster. So just to store the raw files. And then we take the data and then we ingest into what we call as our ETL cluster. So load the data into tables and then process it and so forth. So we have a separate ETL cluster. And then on top of it, we have additional platform services that we offer. So these platform services are kind of, when we put together the solution, there are some shortcomings in the core MPP engine that our customers need. So we built layers of software on top of it. I'm going to explain what those services are in a moment. So on top of this, then you have your traditional analytics applications running, whether it's batch or interactive. So this is a bigger picture of our existing MPP platform. So let's take a quick look at what the platform services we have are, right? At a higher level, right? Majority of these engines, they have some sort of built-in job scheduling and batch management engines, but when you try to integrate it with your whole solution, these things fall short with respect to how do you provide fault tolerance? How do you provide a little bit more sophisticated DAG-based job execution, right? So when the jobs are executing, how do you monitor their performance, right? Whether it's a functional performance or a performance with respect to a feature or whatever, how do you do it? And then when you're done with your data, how do you retire it? How do you take the data out and then add new data sets and so forth? If you have multiple research clusters or multiple production environments, how do you synchronize data between these different environments, right? And on top of it, then you're serving this data to multiple applications or multiple R&D teams within your company across different departments. So how do you provide multi-tenancy for accessing and processing this data? So all these things we had to build in the legacy platform, right? So in summary, if you look at it, the traditional MPP legacy platform is about, you have custom platform services, you have the ETL cluster, you have the RDS store, and then you have underneath the MPP engine. So now, briefly, what are the key challenges we are facing or we have faced so far is scalability of this solution from the volume perspective, from the time perspective, and so forth. There are some issues with respect to if you want to add hardware, some of these engines require you need to add the exact machine, same configuration, homogeneous configuration in the cluster, right? So in addition to that, an operational cost, right? You add more capacity and you add more nodes, you're required to pay more to the vendors that you bought the licenses from. And then this is one of the very important things, at least in my view, is analytics is not about, if you traditionally look at it, people, SQL is the main form of, processing, the analytics information and then consuming it, right? It's more like if you're building something, Hammer is a good tool to have. But as you actually scale out, in the open source world, there are rich set of computing primitives that are available to make your analytics experience or analytics technologies more rich. Things like, you can use streaming, you can use search, columnar store. Combine these technologies with SQL, you can create a lot more sophisticated analytics pipeline. So integration of these things with the traditional MPP becomes a challenge, right? And then, we talked about earlier the cluster operational challenges with respect to preventing noisy neighbors, quotas, throttling, load balancing across different types of loads, integrating secure tenancy, et cetera. All these are the challenges, right? So having said that, so let's take a quick look at our new platform, how we are going to transition from traditional MPP to Hadoop. So this is what I had shown earlier, traditional platform. So let's look at the journey. So for the first thing we're going to do is replace the underneath MPP engine with, think about commodity hardware, right? A set of network, lots of commodity servers, right? And then pick your Hadoop stack, right? Install the Hadoop cluster on top of it. Now think about what functionality that we want to actually replace, starting with. So here we are talking about, let's start with the RDS store here, right? Why do we need to have a separate cluster just to store a passive data that we are consuming on a periodic basis? Why not we use HDFS as a passive store, right? So that's one thing we can do. The second is we are talking about ETL operations. Why would you like to have a separate cluster? Why not we use, for example, with the Hadoop 2x with Yarn, you can control in a large cluster with sufficient enough computational granularity and what you can assign to ETLs, what you can assign to interactive jobs, and so forth. So why do we need to have a separate ETL cluster? So that made us move, take the ETL cluster out, move it to Hadoop, right? Then we have platform services. Let's look at a higher level. What are the things we are doing in platform services, right? So we talked about job management. Can we not use Oozie for that, right? We talked about state transfer between different clusters. How about using dist copy and Falcon for that, right? We talked about issues around tenancy guarding, right? Preventing noisy neighbors and all that stuff. Why not we use Yarn and HDFS ACLs for preventing that? So this made us, maybe we don't need additional layers of software, right? We can actually build on top of what traditional Hadoop ecosystem provides us. So with that, now we can easily build batch and interactive applications on top of Hadoop. So at a higher level, we are talking about you take the commodity hardware, you pick the right set of technologies from the Hadoop ecosystem, use HDFS, use Yarn, and then you can easily transform from your legacy platform to big data. So at a higher level, right? This is the summary. This is how your new platform is going to look like, right? So once you have the platform, this is still evolving, right? So there are some challenges as you scale this platform. There are some challenges that we still need to address. For example, when we have a large number of nodes and large clusters, how do we provision these clusters, right? So we have internally developed a role-based provisioning model where you can take a new node, bare metal node, put it in a rack, go to a CMDB and say that this node is going to become my data node. And then using our orchestration, the technology that we have developed internally, we will provision the bare bones operating system on it, and then install the Hadoop stack, and then configure and tell the Hadoop masters with one click, right? So that's one thing that that helps us. The second is once you have the large number of nodes and then services running in the environment, how do we actually aggregate the logs from these multiple different sources and analyze and debug, right? So we have developed a unified logging mechanism. And then remember we talked about secure multi-tenancy, not only within Hadoop, but also across services within OpenStack and so forth. So to provide that feature, we have developed a thin layer of APIs as part of our platform to provide secure tenancy, right? So that's how, this is the total picture of our platform, all right? So having said that, what I would like to focus is, I want to share with you about, in 4 areas, in detail, the experiences in this journey. The first area is around the cluster build experience. The second area is about the Hadoop stack, picking the right kind of technologies. Third is about using, how do we use HDFS for RDS and then ETL. The fourth is about Yarn itself, how actually Yarn is helping us in this journey. There are actually a lot more details. In the interest of time, I just limited myself to 4, but I'll be happy to talk to you, in this journey, your experience, and share more details off the stage. So let's take a look at the first part. So cluster build experiences, right? let's start with what is the critical ingredient for the cluster, the node, right? So in our case, what we figured out is a single node SKU is very important, and use commodity hardware components. The reason single node is important is you have the flexibility to actually mix and match your components. You can scale them at will, and operations becomes easy and so forth. So on top of that single node SKU mindset, we also looked ahead and figured out that there is a lot of new technologies on the horizon within Hadoop ecosystem, like Spark, and then some memory-based stream processing and so forth. So the node should be able to accommodate, not today, but maybe a year from now, right? So if we have to have memory-based workloads, we should be able to add memory to it. That means when you pick your node, look at your motherboard and make sure that it has enough room for expansion capability. The third important thing in picking the node for us is this, what I call as spindle core and LAN network ratios. It is not like a complete science, but it is also some trial and errors. What we figured out is the ratio here, 1 spindle to roughly like 2.5 cores. These are the empty cores, multi-threaded cores. And then roughly like 1.5 GBS of network bandwidth is the ratio that what we figured out is like ideal for us. There's a lot of details and math behind it. I'll be happy to chat with you offline, but let me give you just idea about why this is important. Let's imagine that you have 1 spindle, right? You have you need to read a block from that spindle. So typically most of these commodity SATA drives, you can read about 125 megabytes per second. So that translates to about roughly a gigabit capacity that the disk can pump the throughput out. So if you have to read this block and then send it to a compute slot, which is on a remote machine, how much bandwidth you need? Roughly a gigabit per second per spindle. So typically when we plan our network, you don't actually saturate the network with 100% utilization. We pegged it around 60. So that translates to like 1 spindle. If it is fully operational, it takes roughly like 1.5, a slice of network bandwidth, 1.5 gigabits, right? So we did the same math around a spindle to compute slot ratios and so forth, and I'll be happy to share any further details later on. Then other best practices around mixed workloads using Yarn. So what we figured out is large clusters are very important. It is actually very easy to, in large clusters, you can actually deploy different types of workloads and load balance between different types of workloads and different types of tenants as well. So that's another best practice that we have. And lastly here, under the platform features, I already talked about a centralized monitoring, logging, and aggregation mechanism we developed. Here we use the Elasticsearch, ELK is Elasticsearch, Logstash, and Kibana. That's the stack we used to build the centralized log aggregation framework. Similarly, the role-based automated provisioning, we used ITOP and Foreman for building the orchestration layer in the environment. So here, in summary, the best practice is focus on the key node, the node configurations. Think about large clusters and think about automation, especially the things that you don't want to do quite often, right? So now we are done with the best practice around how we pick and build a cluster. The next thing is the software stack, right? So our goals here is we want to use open source platform. Then we want to use scalable distributed processing. We looked at our workloads, and most of them are built around traditional SQL, right? Then we looked around what are the options we have in Hadoop ecosystem. This was one of the very interesting and toughest decisions for us. There are 2 technology choices that are available today in the market. One is based on a primitive or on a technology direction where what I call as like distributed query engines like Impala and Presto and so forth. They fall in that. The idea there is you take the query, somehow figure out where your data sets are and distribute the computation and get the work done. So these are ideal for fast response queries. And the other one is you take the existing MR environment, make it faster. Hive is an example of that, right? So in this technology spectrum, what we are talking about is, let's solve the scale problem first, and then try to run this technology faster, and then optimize it for speed later on. So on one side, one technology stream is optimizing for speed first, other side is optimizing for scale first, and they're trying to converge. So our dilemma was to figure out which side to go, and so that they will come to a midpoint where we need both speed and scale, right? So the way we went about this is we evaluated, we took 15 of our representative workloads, basically including some complex joins and shuffles and so forth. And then we set aside some criteria, right? So what is important for us? For us, the scale is important, and then the technology has to function first, and then it has to be stable, and then the performance comes later. Performance is doing it faster, right? So we set aside some criteria for us, and then ran some test case across both spectrums of tools. And then where we ended up is we figured out that Hive is the one which is meeting our needs, and with the Thales, definitely it became a very obvious choice. The performance is at least meeting some of our goals, and then it is in the right direction. So we made a big bet on Hive and Thales, and then chose this technology for our Hadoop stack, along with the other technologies like HDFS, Yarn, Oozie, Falcon, and all of the things that I outlined before. So with that, let's go to the next layer of best practices that I want to talk about. So now we have the infrastructure, then you pick the technology. Let's look at what we want to do with RDS and ETL together. So here, raw data store, right? So remember we had mentioned about the platform. So we have platform APIs for ingesting the files from remote locations. And why do we need to have the APIs? Because we wanted to provide secure multi-tenancy, replication, and reliability on top of the platform. And then convert the incoming data into raw data stores and store it in Hadoop, and then do ETLs on top of it. This is very interesting thing. What we figured out is initially we started having, if you look at the path 1 here, we ingest the file, and as part of the RDS, what we are doing is taking our incoming files, which are in different formats like ZZ format, tar files, zips, and so forth. We wanted to store these files, which typically in a year range to petabytes, right? We want to compress them in a space-efficient manner. We figured out that BZ2 is the BZIP2 is the right thing. So we needed to convert these incoming files into BZ2 format. So we evaluated 2 options. One is just get the file into the system, and then have a node outside the cluster that converts unzip and then encode it back into BZIP2, and then ingest into HDFS. So that took roughly, like on a sample of like 5 gig file, roughly 28 minutes. And then we tried the same thing with instead of doing the ZZip to BZIP conversion right here, we did with a single mapper inside the cluster. It took us 5 minutes, roughly. It's very surprising for us. So when we started analyzing why is it taking 5 minutes, where is the speed up coming from, right? So you remember we talked about the spindle core and network ratio we have. So what's happening is as the ZZip file gets into the cluster, it gets split into smaller blocks. Let's say the block size here is 512 MB. It's getting spread across data nodes, right? And then when you span a single mapper, what the mapper is doing is trying to read these blocks in parallel from multiple nodes simultaneously into the memory. This operation on a single machine was happening on a single spindle. So that's where the spindle became the bottleneck, whereas here we have the multiple nodes doing their stuff, right? So now we have the operation being done parallel ingest into the mapper. You convert your ZZip to BZ2, and then do the same operation on the reverse side, write it back, parallel write. So that's where the speed up is coming from, right? So that's another best practice. And then once we solve the RDS problem, the raw data store problem, then we looked at our ETL thing. right? So what is ETL? So once we ingest the files, we store it in the RDS, we need to load these files into Hive tables, right? So we chose ORC format for keeping our data inside Hive, right? So that transcoding requires computation power. So we created separate queues for ETL within Yarn. So in summary, net, if you look at what we are doing here is using, we don't have any special software here. We're using HDFS, we are using Yarn just to finish our, we eliminated 2 clusters just to finish our RDS and ETL process. So next, the last and most important thing I want to share with you is about Yarn itself. So here, think about in a large cluster, you have to do ETL jobs, and then you have to satisfy your ad hoc queries, and then you have to satisfy your batch applications. So in each of these applications, the application requirements are different. So let's take ETL jobs. What do they need? ETLs require guaranteed throughput. So for example, you're ingesting on an hourly basis, let's say 40 terabytes of data, and the next batch of data comes in next hour. So you need to guarantee and make sure that before the new data comes, your existing batch need to be stored in RDS as well as transcoded, right? So that means you need to have guaranteed throughput, and it's a window-based computing, right? What does your ad hoc queries require? So somebody is sitting at their desktop making some ad hoc query and analysis using Pig or Hive SQLs, right? So they require, as soon as they submit the job, low latency. That means their job should go to the cluster, transform into MR jobs, and then get the work done. They want fast execution. What do batch jobs need? They kind of in between, right? They need throughput. They need guaranteed execution. So we have these multi-mode jobs we have in the cluster, and then you have multi-level. Now you take these multi-mode jobs, apply across your multiple departments, having multiple projects and users. How do you balance these 2 things in a large Yarn cluster, right? So that's the key question, that's the key challenge that we faced with. So what we did is, what I'm going to explain is an approach that worked for us. Not necessarily the numbers and the outcome that I'm going to share with you is valuable, important to you, but the approach is very important. So here is what we did. So the step 1 is, it probably takes a day or 2 job. You model using your spreadsheet. First step, figure out, list down all your ETL jobs, right? So for each ETL job, figure out, how much data you are ingesting, what is the size of the file, right? What is the service level objective, SLO, that you need this file to be stored or ETL'd and transcoded within the time. And then from there, apply, there's a lot of literature out there in the, in the community. You apply, how to translate that requirement into number of map and reduce tasks. And then that's the step 2. And then you also know about the amount of data that is going to HDFS cluster. So the modeling is about take this set of your representative ETL jobs, figure out the number of map reduce tasks and the storage that you need for that. Repeat the same thing for your batch jobs, repeat the same thing for your ad hoc jobs. So with this, what you get is roughly what your application or workload computing model is, right? Now take that and then look at Yarn, right? So one good thing about Yarn is it provides hierarchical allocation of resources. So you create a resource model. This is just again a representative model that we started with. And then here the root queue is the 100% of the cluster resources you have, and then allocate at the second level, at the ETL level, different types of allocations, maybe ETL queue, depending on the number of slots that you required in the previous spreadsheet that you figured out, certain percentage. Let's say ETL is 40, batch is 30, ad hoc is 30, something like that. That depends on your previous one. And now within that specific category of ETL loads, then subdivide that to your projects and tenants and so forth. And then run the representative workloads and run some sample tests, and then figure out what is the utilization of your cluster is, what is the average latency, and then what is the throughput for these jobs. repeat this with different variations. Change the model here. The difference is instead of having the ETL and batch at the second level, now it is at the third level. You promote the projects to the second level. So this is another variation you can have, right? So the third variation you can have is a mixture of the first 1 and 2, where maybe ETL is important, batch is important, keep them at the second level. Ad hoc is very fluctuating, so then push it to the third level and then see what kind of loads you get it. So what we figured out is we ran our representative test cases against these 3 models, and what we figured out is in our case we got very optimal number in terms of our higher cluster utilization is around 75%. Average job wait times for our ad hoc queries is roughly like 2 minutes. Throughput is good. So that's how we decided how we do the modeling for Yarn, right? So with that, I would like to wrap up. Here are the key lessons. So in this journey, the optimal solution is not about optimizing in one area, but you look at the entire stack of your infrastructure, your software technologies, how you manage data, how you configure Yarn, and come up with an optimal solution. So for us, for you to do that, and obviously we need to have good monitoring and management solutions. The approach we took, the mindset we have is start smaller, but iterate faster. Whenever you're in doubt, just make data-driven decisions, and obviously keep customer use case in perspective. So finally, here is a summary, right? The journey from MPP to big data it's a incremental transition. It's actually a journey towards open source distributed computing. Other key lesson is use your clusters, you take advantage of Yarn, make the computing very uniform. Use open source where possible, and share your ideas, and most of all, have fun while doing so. Thanks. Any questions? Yeah. Go ahead.
I saw your single node SKU.
Yep.
You mentioned commodity hardware.
Yep.
I wonder if you can go into what your definition of commodity hardware is, and go into that. The second question is, you can follow up. You mentioned the transition from MPP to Yarn.
Yep.
MPP to Yarn. Did you run both on the same set of clusters? Did you have 2 separate clusters, or did you move one off and move the other one in?
Sure. So let me address the second one first. So there are separate clusters. So they are separate environments and they are separate type of hardware. In terms of the first question, right? So whenever we say commodity, right, it's a very relative definition. Commodity is basically something very cost effective that's available in the market mainstream. An example is, let's take a disk, right? So do you want to use very expensive SAS type, nearline SAS or type of things versus SATA, right? So SATA 7200 is what we found as commodity. Same thing with your networking, same thing with your hardware infrastructure. That's the mainstream. Anything you want to?
Also to add to that, so what we found out from our MPP experience early on was that the particular MPP solution that we had in hand was very sensitive to any of the disk to CPU ratio, the memory, even CPU clock cycles. If you had any change between the hardware, your MapReduce jobs, any distributed work that you were doing went for a toss. So that's where the Hadoop system really started to kick in value for us, where year after year, if your Dell, your HP, any of them come along and say, well, we are just going to do EOL of our hardware, guess what? You need to add more nodes in the MPP world. Well, you'll have to replace all of your hardware, right? Because you just can't add just the newer generation hardware in there. So that's where it really added value. And it was, as Srinivas mentioned, it was completely separate clusters.
Good question. Thank you. Any other questions?
What tools did you use to move the data actually between them?
To repeat the question, what tools did we use to migrate between MPP and the current cluster itself?
So we looked at a few tools like Scoop and so forth, but what we decided effectively is, at least at our scale, we're talking about multiple hundreds of terabytes to petabyte, is take the raw data sources, ingest them directly, and then use the native Hadoop tools like Hive and MR and stuff like that to transcode the data. So you have two flavors of the things existing, but we started with the source. Next one. Okay.
This means Scoop and other traditional tools to scoop data of databases was slower than ingesting the raw.
Yes, that's true. The main reason is, yeah, at scale, it is very not appealing. Yeah.
It's not clear to me from MPP was an appliance type of MPP database or was something you built?
So it's around, it's a cluster. You can consider it like a cluster appliance, and on top of it, we build our additional solution on top of it.
Okay. And if you were to provide advice to large corporates, I want a clear-cut answer. Would you recommend to migrate completely? Because there is this school of thought from MPP, large data warehouse players that are saying, it can be combined atmosphere, but for you it's not. So what would you say?
I'll take that, and I'll give you the traditional MBA answer, it depends. No, that's what you're going to hear from any vendor or any professional services. Any person that you talk to on the Hadoop world, you're going to hear the "it depends" answer. And the reason is because it actually depends on your workloads, right? What are your use cases? What are your users familiar with? Are they familiar with more SQL? And do they need certain level of SQL compliance, or rather SQL standard? And if that is the case, then Hadoop might not be an option for you, just because your users are going to look at it and say, no way, I'm migrating over here, right? You would have built this huge platform and it wouldn't be of use to your users. So it actually depends on your use cases.
Thanks, all. I think we got a signal that running out of time. So I'll be staying here along with Rupesh. So we'll be glad to